Today I'm going to talk briefly about quartz crystals, why they are important, their properties and structural features, as well as applications. Quartz is an abundant natural mineral with a chemical formula of SiO2. It's distinctly recognized for its noticeable trigonal crystal system. Many varieties of minerals form in the Earth's crust, but quartz is the most abundant. Why? Silica, or silicon dioxide, is the most prominent constituent of sand. This is mostly found in the form of quartz. Oxygen and silicon are the most abundant elements in the Earth's crust, making up around 75% of it. Other elemental contributions include iron, calcium, potassium, sodium, magnesium, and so on. In addition to silicon and oxygen being the most abundant elements, silicon dioxide is also the most abundant mineral in the Earth's crust. It accounts for about 20% of the Earth's crust and 12% of the Earth's surface. It is also the main constituent for many types of rocks. Quartz and glass have very similar elemental constituents, although they possess invariably different properties. Quartz contains around 99% silicon dioxide, whereas glass usually only contains up to around 80%. This is the most common type of glass we use for things like containers. It's comprised of roughly 75% silicon dioxide, sodium oxide, and calcium oxide, as well as other impurities. This is called soda-lime glass, and we can see a greenish hue from the impurities are present in the structure. Glass is also an amorphous material, meaning that it has a random arrangement of molecules, whereas quartz is a crystalline solid, so it has a periodic arrangement of unit cells. Therefore, it's a symmetrical structure. There's a lack of periodicity within the glass structure due to the random arrangement of silica units. Quartz possesses a periodic crystalline structure with long-range order. These differences in fundamental structure correspond to varying properties. Glass is isotropic, meaning that it has the same physical properties in all directions. The properties of quartz are dependent on the direction of the crystal. Glass cannot have a particular melting point since it's not a crystalline material. The structure of quartz was first observed by Bragg and Gibbs back in 1925. It's comprised of SiO4 units in a tetrahedral arrangement. So now we ask the question, how do we form glass from sand or quartz? Well, there's still quite a lot of confusion about whether glass is actually a liquid or a solid. And the truth is, it's actually neither. The best way to describe this disordered arrangement is to think about cooling water so quickly that it doesn't actually have time to form a full crystalline structure like in ice. And this is essentially what's happening when we are converting quartz or sand into glass. Sand is mostly comprised of silica crystals, which are small but resilient. As magma is cooled within the Earth's surface, different materials solidify at different temperatures. Quartz is one of these minerals and forms small grains in between the larger minerals. This is essentially how sand is formed. This sand is heated to its melting point at around 1700 degrees Celsius. When the melted sand cools back down, a complete transformation in the crystal structure has occurred, where the crystalline form is now rearranged into the amorphous form, i.e. glass. Silica tetrahedra are fundamental for silicates to form. Other examples of silicates are feldspar and pyroxene. They all have slightly different crystal structures and therefore different physical properties such as melting points. The crystal structures can be determined by X-ray diffraction. Quartz itself comes in many variations, usually due to trace elements being present in the crystal structure. These have significant applications in jewellery due to their appealing colours. However, they also differ in terms of chemical properties. Amethyst is purple due to high energy radiation, for example gamma rays, from radioactive sources and iron impurities built into the crystal structure. The radiation causes iron 3+ ions to replace silicon in SiO4 units, losing an electron and forming iron 4+. This is the current theory used to describe the colour of amethyst. Are there any more applications of quartz? Perhaps the most fascinating quality of quartz is the fact that it's piezoelectric. This means that it generates an electric charge in response to an applied mechanical stress. Also, if you pass electricity through quartz, it vibrates at a precise frequency. This is why quartz is used in watches and clocks. Electricity is passed to the quartz from a battery. The crystal then oscillates at a precise frequency. This is exactly 32,768 times each second. The circuit counts the number of vibrations and uses them to generate regular electric pulses, 1 per second. Hence, we have a quartz watch or clock.